This is your Chapter 6, Section 3 notes, solution to polynomial equations. So, at the very beginning here, we're just going to be able to, or most of them anyway, you'll be able to factor them and use the zero product principle. So, you'll be asked one of these three things. They're basically all three asking the same thing, just in different ways. They all kind of mean the same. So we have some function p of x, and this is what it's equal to. It's this times this times this. So it's a factored form of a polynomial. So part A wants us to know what are the zeros of the polynomial. Well, zeros mean it's the things that makes this p of x equal to 0, right? Which is what that says right there. And since we have multiplication, this is this times this times this. If any one of these three things is equal to 0, for instance, if x minus 1 is equal to 0, or if x plus 2 is equal to 0, or if x plus 5 is equal to 0. If any one of those three things is equal to 0, it doesn't have to be all of them, just any one of them. If this is equal to 0, well, 0 times 0 times anything is 0, and then 0 times that is 0. So if this first piece is 0, then the whole thing is 0. If the second piece is 0, then the whole thing is 0. Or if the third piece is 0, then the whole thing is 0. So basically what that does is it gives us three equations to solve. Alright, add 1 here to both sides, and I get x equals 1. Or subtract 2 from both sides, and I get x equals negative 2. Or subtract 5 from both sides, and I get x equals negative 5. Alright, so here are the zeros of this function. Now I can write them in a couple different ways. I can write what I just did here, x equals 1, x equals negative 2, or x equals negative 5. Or I can do it in like a solution set notation. Alright, and usually you start with the smallest and make your way to the biggest. Doesn't have to be that way since it's a set, but that's kind of the standard. So that's the typical way to write it. But the thing I want to tell you is that part B is the same as part A because they're asking for the same thing. The zeros of this polynomial is the solutions that make the polynomial equal to 0. That's what it means to be a 0. Right, so the answer to part B is the same as the answer to part A. X equals 1, negative 2, and negative 5. Alright, and then C, what are the x-intercepts of the graph y equals that function? Well, I'm going to throw it into the calculator and you'll see I've got them in here. When I graph this, I'm going to hit zoom 6 just to come back to the main window. Alright, there's negative 1, 2, 3, 4. There's negative 5. There's negative 2. There's positive 1. Alright, so we get the exact same things as we did before. And now those are the x-intercepts of the graph of that thing. So for C, it's the same thing again, but since they're x-intercepts, I'm writing them as point pairs. So negative 2, 0, negative 5, 0. Alright, pay attention to the problem that you're doing on your MyMathLab homework, because sometimes it'll take x equals 1, x equals negative 2, x equals negative 5, but sometimes, especially when it's asking for intercepts, it may want it as a point pair. But just make sure to read the problem carefully. Okay. Big point of this first slide though is that all three of these things are saying the exact same thing. They're all ways to ask for the same thing. The zeros of a function, where the function is equal to 0, and what are the x-intercepts of the graph of the function, all mean the exact same thing. Basically, just depends the context would be the only way we would decipher between the three. Alright, so a lot of the times you'll be given an application type problem but you're doing the same thing that we just did on the previous page. Here's a volume formula. This is similar to the lab we did in class. So I'm going to cut X off of this thing. I got a 24 by 24 inch square, and I'm going to cut out the corners, and that's going to leave me this cross-shaped thing, and then I'm just going to fold it up. Alright, and it forms this box. And what they're saying is, if this is 24 inches long and I cut X off of this side and X off of this side, then I end up cutting 2X off of each of those 24 inch sides. So I get this 24 minus 2X by 24 minus 2X by X box, and that's our volume formula. Okay. Alright, here's some questions. Use the factors of V, use these factors to find the values that give find the values of X that give a volume of 0. Okay, so the volume of 0 means that V equals 0. So when is V equal to 0? That's just like we were talking about. Find the zeros of this polynomial. So one of these things is 0, either 24 minus 2X, which appears twice, so I only have to solve it once, or the easy one, X equals 0. Alright, well, if this one's equal to 0, then we're done. There's one possibility. If this one equals 0, then we add 2x to both sides, and we get 24 is equal to 2x. Divide both sides by 2, and we get x is equal to 12 inches. Alright, now let's think about this for a second. Why are these our two solutions? Well, if I cut off nothing, then I have a 24 minus 0, a 24 by 24 inch piece of flat board. Okay. And what can I do? I can't fold up anything. I didn't cut off any pieces, so I can't fold up anything. So it has no height. When x equals 0. Alright, since there's no height, there's no volume. Okay, so that's why that one's showing up and given a volume of 0. What about 12? Well, when x is 12, that means we cut, here's halfway, we cut that out from this side, so it's gone. Well, what else do? We cut this out, we cut this out, and we cut this out. Well, now we can't fold anything up into a box because we cut everything apart. Okay, so that's why we're getting 0 volume when we cut 12 inches off. We don't have anything left, basically. Alright, so there's my two zeros for volume. Alright, what input values make sense for this problem? That is actually result in a box. Okay, well, anything between 0 and 12. Like we just said, if we cut off nothing, then we don't get a box. If we cut off half the length off of every side, then we don't get a box. But everything in between should give us a box. So 0 inches all the way up to 12 inches for x. Now graph the function using the input values that make sense for the problem found in part B. Alright, I'm going to put this in my calculator. So there's my 24 minus 2x, 24 minus 2x times x. Now I'm going to go to my window, and we said that we're going to let the x-men go to the x values go between 0 and 12. Okay, and then just for the time being, I'm going to leave this the way it is just to help us find a window. But when you graph it, I mean, we just determined that it's between 0 and 12, so we're going to put that in there for x's. Graph it, see what everything looks like, and figure out how we need to adjust our window. Alright, I can't see anything in here. I see it come down, so I know everything's above it. So I'm going to go into the window. I can adjust this. I know it's not going to be any negative values here because we're going to get volume. It's going to be positive. But just to have that line in there, I'm going to put -2 for my y-min. Alright, and let's make 1100 for my y max, and I'll make the y scale 100, and that way we should be able to see all this. So hit graph. So there it comes, there's our peak, and then it comes back down and then it hits again. Alright, so I'm going to put that in here. Alright, and then again, this is 0 here, this is 12 up here. Alright, and then this was 0 for y all the way up to 1100. Alright, and each tick mark was 100. Alright, so we graphed the ones that made sense for the problem. Now, did it go beyond that? Yeah, it went beyond that. It came back up and it, did all that. Went back up after that, but we're not concerned with what happens after that because it doesn't make sense to go beyond 12. You can't go beyond 12 in this problem. Alright, then D wants me to use technology to determine the size of the square that should be cut to give the maximum volume. So find X right here. Find that X coordinate is basically what we're being asked to do. Alright, so we've got it graphed here. This means go to our calc menu, second trace. So for us to find a maximum, that's what we're trying to do here, maximum volume. We'll pick option 4, left bound, right bound. So remember, go to the peak, get as close as you can, and go a little bit to the left for left bound. Go to the peak again, go a little bit to the right this time for right bound. Alright, and then come back close to the peak for your guess. Alright, so there's our answer. Now, notice your calculator does this approximation stuff. Okay, it does a numeric solve. It's not setting up an equation and solving it by hand like you would. So it's not getting 4 even, it's getting 4 in this really small decimal. Okay, it's important for you to understand that this is 4. This is your calculator using the numerical method to find that number, and it's getting really close to 4, but this is 4. Alright, so for this problem, cutting 4-inch squares off each corner, maximizes the volume at, again, what was that? 1024 square inches. Alright, and then something you've seen here before. This is a cost function measured in thousands of dollars. Make sure you read those units. And X is the number of hundreds of units produced. How many units must be produced to give a total cost of 45,000? So that means the cost is equal to 45,000. Right? It's measured in thousands, so we just let C of X equal the 45 here. Don't worry about the zeros because that's taken care of right there. So 45 equals x cubed minus 12x squared plus 3x plus 9. Okay, now what do we want to do? We want to set it equal to 0 and then factor it if we can. So we get x cubed minus 12x squared plus 3x minus 36. Alright, now when we have 4 terms like this, 1, 2, 3, 4. When we have 4 terms, that means we use grouping to factor. Alright, and if it's been a while, the way you do grouping is if you have a plus sign in between your second and third term, you just literally put parentheses around the first two. Right, if you've got your polynomial in descending order like this, 3, 2, 1, constant, and then put parentheses around your second your third and fourth terms. Alright, and then after you've got them grouped, you factor the GCF from each group. Alright, so the GCF here is x squared. So I pull out an x squared and I get x minus 12. Alright, and then in the next group, the GCF is 3. So I pull out a 3 and I get x minus 12. Now, your goal here is you want the same factor left in the parentheses if you're going to be able to use factoring by grouping. This is still equal to 0. Now, once you've done that, you pull this common factor out. X minus 12 is common to both. So I pull it out, and what's left is an x squared plus 3. Alright, now what we do from there, we've got something multiplied together equal to 0. This times this is equal to 0. So x minus 12 could be what's equal to 0, or it could be that x squared plus 3 is what's equal to 0. Well, let's think about it for a second. This one on the left is easy to solve. If this is the case, add 12 to both sides and we get 12. But here, I'd have to subtract 3 from both sides to get this x squared isolated, and look what happens. I get a square equal to a negative. Okay? This is going to end up being imaginary. Alright, and if we were, doing regular old algebra, we'd say x equals plus and minus I times the square root of 3. Okay, if you remember back to doing the quadratic section. But we're not doing regular algebra, we're doing applied algebra. So that cannot be a number of units produced. We can't produce an imaginary number of units. So it has to be that this is our solution. Alright, so what does that mean again? It will take 12, again, x is measured in hundreds, so 1200 units for the cost to equal $45,000. Alright, so don't forget to put your hundreds in there. Make sure you're reading your units correctly. Alright, the root method, that's kind of what I used here at the end here, even though this was an imaginary. This right here over to this side, this is the root method. What the root method basically says is, if you have just x to the n equals a constant, you don't have any other terms, you just have x to some power equals a constant, you can take the nth root of both sides, right, and solve the equation. Now, if n is odd, then you don't have to worry about plus and minus. It's just the nth root of whatever c was. But if n is even, 2, 4, 6, 8, 10, 12, then you do need a plus or minus. Okay, because remember, negative times a negative, or an even number of negatives, is also equal to a positive. Alright, so if I'm doing this problem, part A, x cubed equals 125, that's this scenario with n being odd. So for that I get x cubed equals 125. We solve it via the cube root. So we're going to take the cube root of x cubed is equal to the cube root of 125. Okay, if this is equal to this, then their cube roots are equal. Alright, the cube root of a cube, we just get x. And then the cube root of 125 is 5. Now I just happen to know that the cube root of 125 is 5, but you can go to your calculator a couple different ways. One, underneath the math button is the cube root, so you could come down here to cube root, and then just type in 125. Or if you remember from the power section and the exponent section, the cube root is the same thing as the 1/3 power. Alright, so either one of those will work. Alright, for B, we want to isolate the x to the 4th. If you notice, the root method works when there's nothing out in front of the x. Okay, so if I have something out in front of the x, I'm going to divide it away. So I'm going to divide both sides here by 5. Alright, and I get x to the 4th equals 80 divided by 5 is 16. Alright, and then if n is even, then we do need the plus and minus. So x is equal to plus and minus the 4th root of 16. Okay, so x equals plus and minus the 4th root of 16 is 2. So I have two solutions, x equals positive 2 and x equals negative 2. Or I could write it in solution notation like this. Alright, if I want to check this solution, or if I wanted to do the 4th root, if I didn't know what the 4th root of 16 was, you can do that again with the math button, but you have to press the root first. So it's the 4th root, so I'm going to press 4, and then math, and then this one right here with an x there, that means any root you pick. So the 4th root, I'm going to pick the x root. So that's the 4th root of, and then tell it 16. Alright, and we get a 2. Alright, so if you wanted to do it that way, again, you could also do 16 raised to, this is the 4th root, so that would be the 1/4 power. Okay, both of those methods work. Alright, now again, we just have to remember to stick the negative out in front of there. It's not going to tell you, it doesn't know that you're solving an equation, that you're having to do this root for the purpose of solving the equation, so you're going to have to know to do that plus minus. Alright, and then part C, let me extend this down. Alright, part C wants us to do the 4th root of x squared is equal to 18. Alright, divide both sides by 4. Alright, 18/4, that'll reduce down to 9/2. So I have x squared is equal to 9/2. Alright, same thing as before, I got an even power, so I'm going to need a plus and minus, so x is equal to plus and minus the square root of 9/2. Alright, coming down here, x equals plus and minus the square root of 9 up top. I can, well, let me show you this. I can split that up into square root of 9 over the square root of 2. That equals plus and minus the square root of 9 is 3 over the square root of 2. Plus and minus, that's like 3 square root of 2, and then I'm going to multiply to rationalize that denominator. I'm going to multiply top and bottom by the square root of 2, and that gives me my final answer is 3 square root of 2 over square root of 2 times square root of 2 is 2. So there's my final answer there. Alright, you can check this stuff with your calculator. Go to like y equals, or in this case, if you do 3 times the square root of 2, close parentheses, divided by 2. Alright, store that as x. Alright, hit enter. And then come over here and rewrite the original equation, which was 4x squared. Hit enter. There's 18. Alright. Now go back a couple of steps. Second enter. Remember that takes you back to previous entries. And then go up here in front of that 3. Second delete makes that an insert button. insert a negative, store that as x, and then again 4x squared, write that, and you get 18 again. Okay, so those things do work. Alright, and then also remember, anytime you're doing an equation, left side 4x squared, right side 18. Alright, graph it. I'm going to hit window, -10, +10, and then this time I need to make my y max. I'm going to make it go from -20 to +20. Alright, and I'm going to hit 2 and then graph it. So there's our 4x squared. There's our intersection with 18. Find those intersections. First curve is the parabola. Alright, second curve is the y equals 18 line. Guess right about there. Alright, and then we see the decimal version of that number. Okay, so the thing about this, using this intersect feature, is it will find a decimal if it's some kind of radical like this. So you gotta know how to do it by hand if I ask you to find it exactly. Alright, last example here in this chapter or this section. Same thing we just did basically. Here's a polynomial that models this thing. You're not going to be able to factor this and get something down. So what you're being asked to do here is throw this in your calculator and use the model to estimate graphically the year after 1980, so that's what x is representing, in which the number of arrests fell to 234 per 100,000 juveniles. That's what y is equal to here. Okay, so we're going to set this equal to 234 and find that. So we're going to do just like we did a second ago. Alright, so in the first one I'm going to put the original function, and then the second one I'm going to put in the corresponding year. Alright, so I've got the original function right here in my y1. I've got, we want to know where it the number of arrests fell to 234, so we've got that in our y2, and then I've made my window, notice 0 to 35, right? 1980 is x's years after 1980, right? It's 2012, so I just made it go to 2015. Alright, and then an x scale of 5, minimum y0, just because it's got to be positive, so we're looking for things above the x-axis. And then the max, I did 500, just kind of played around with it until I found the right window. So when I graph that, I get this. There's that peak that they were talking about, 1994. Alright, and then there is that 234 line. So there's what we're looking for. So trace, find that intersection. First curve is our cubic model. Second curve is not really a curve, it's that horizontal line, and then there's our guess. So 20 is the year, and that's years after 1980, so that would be in the year 2000. So approximately the year 2000. The number of arrests fell to 234 per 100,000. Alright, so there's your examples in this section. Use technology if it allows you to. Alright, so when you see estimate graphically, or obviously use technology, then that's when it's asking you to use your calculator and that intersect feature to help you with the solutions. Okay. Okay, but there'll be some of them, like you have to do up here, where we want you to solve by factoring or do it by grouping.